Hi everyone, this is BB Singme, and in this video I am going to discuss about the design of cotter joint. Cotter joint is the machine element which is also subjected to static type of load. In this chapter we are discussing about the design of machine elements against static load. In that we have discussed the design of knuckle joint, design of turnbuckle in the previous videos. Okay, so do subscribe for the upcoming videos of machine design. So a cotter joint is used to connect two coaxial rods which are subjected to either axial tensile force or axial compressive type of force. Cotter joint is used to connect a rod on one side with some machine part like crosshead or base plate on the other side. It is not used for connecting shafts that rotate and transmit torque. So it is not meant for the transmission of torque. It is only meant for the transmission of axial tensile force or axial compressive type of force. These are the typical applications of cotter joint. It is used as a joint between the piston rod and the crosshead of a steam engine. It is used as a joint between the slide spindle and the fork of a valve mechanism. It is used as a joint between the piston rod and the tail of a pump rod. It is used as a foundation bolt, mainly used in fastening heavy machines to foundations and construction. So this is the figure of cotter joint. Here you can see that only three parts are there. One part is called as a spigot, one is called as a socket, and these two parts, spigot is going to fit inside the socket, and these two parts are connected by means of a cotter. The cotter is having a weight shape. It is having some thickness. It is having some height. Okay, so here we are going to calculate the dimensions of socket, spigot, and cotter. Okay, so usually the cotter joint is used for the application of tensile and compressive type of load. Here I am going to consider a tensile. For the tensile application I am going to calculate the dimensions. Okay, so here you can see that in the figure, this is the cross sectional view. Okay, this is the top view. In the top view you can see the assembly of spigot, socket, and cotter, and in the front view also, this is the portion of, here you can see the hatching lines. Okay, this is the portion of spigot. This is the portion of socket. You can see that the orientation of hatching lines is little bit changed, and this is the unhatched portion, or the portion which is not having the hatching lines, because it is the thin portion. It is actually the cotter. Okay, in the side view here you can see that the socket and spigot both are having circular cross section, and in the side view you can also observe the thickness which is represented by the letter T. It is the thickness of this wedge shaped cotter. Okay, so here we are going to calculate every dimension. So first of all, let us see here. After the application of force P, you can see that there is a possibility of failure of components, that is the parts of spigot, cotter, and socket in various manner that we are going to discuss in the next slides. Okay, so here the smallest diameter, it is nothing but the diameter of rod, socket rod and spigot rod. Socket rod is A and spigot rod is B, and both are having the diameter which is represented by the letter small d. Okay, next is the outside diameter of socket. Okay, so here you can see that this is the outside diameter of socket, and it is represented by, in the top view you can see that it is represented by the letter D1. Next is the diameter of spigot, or it is also inside diameter of socket. It is represented by letter D2. Here you can see that the spigot is having a solid rod shaped structure. Okay, so its outside diameter of spigot is D2. Okay, here you can see that, and it is also inside diameter of socket, because the socket is having some hollow shape structure inside. Okay, inside which the spigot is going to fit like a plug. Okay, so D2 is the outside diameter of spigot and inside diameter of socket. Okay, D3 is the diameter of spigot collar. So here you can see that the spigot is having the collared shape, and its outer diameter, here you can see that it is represented by letter D3. D4 is the diameter of socket collar. socket collar is also having socket is also having a collar shape. Collar is provided. Its outside diameter is d4. Here you can see that it is represented in the side view, a circular shape. Okay, so it is the outside diameter of socket collar. A is the distance from end of slot. So here you can see that A is the distance from the end of slot to the end of spigot on the rod along the axis. So this is the distance. B is the mean width of cotter. Okay, so the cotter is having the taper shape. At the topmost it is having maximum width, at the bottommost it is having minimum width. So at the middle portion, the portion which will be inside the spigot and socket along the axis of the spigot and socket, here you can see that the width is measured and it is the mean width. Okay, it is represented by the letter B. So B is the mean width at this portion of the cotter. C is the axial distance from the slot to the end of socket collar. So here you can see that C is the distance. Okay, actually the spigot is having some rectangular slot inside it. Okay, inside which the cotter is going to fit. Okay, so from this portion, C is the actually width from this point to this point. Okay, so here let me show this, let me highlight this. So this portion is having some width, it is represented by letter C. Here you can see that. Okay, from this slotted portion, from this point to from this point where the collar started. Okay, again T is the thickness of cotter. Here you can see that the cotter is having thickness. So this is the thickness. Their thickness you can observe in the side view. In the side view you can see that thickness of cotter. T1 is the thickness of spigot collar. Here you can see that the spigot is having collared portion. Okay, so this is the thickness of spigot collar. It is represented by T1 in the cross sectional view. You can observe that. L is the length of cotter. In the side view you can see that this is the actually length of cotter and it is represented by letter L. So this is the length of cotter. So all these dimensions we are going to calculate in the design process. So let us discuss about that. So here, after the application of force of magnitude P on the rod of socket and on the rod of spigot, the rod is having the diameter small d. Okay, so after the application of tensile force, there is a possibility of failure of rod along this cross sectional area. Okay, at this cross sectional area and also at this cross sectional area. Okay, in the tensile manner that these rods are going to fail. If we'll take a side view of this, it will be circular. Okay, and by using the formula, by considering the tensile failure or by considering the tensile stress will be get induced after the application of force. So the formula will be sigma T is equals to P by A, where P is the applied force. Okay, A is the cross sectional area of rod A and rod B. Okay, so here A will be pi by 4 d square, where d is the diameter of rod A and rod B. Okay, d small d is the diameter. Okay, so by using this formula we can calculate the diameter of rod A and rod B. I am going to rewrite this equation in terms of d. It will be d is equals to root of 4p divided by pi into sigma t. Okay, so here p is the applied force, sigma t is the permissible tensile stress or permissible stress in tension for the material of rod A and rod B. Okay, so once you will have the value of p and sigma t, you can calculate the diameter of rod. Okay, because the rods are only subjected to axial tensile type of load. Okay, so by using this formula we can calculate the diameter of rod. So in the previous slide we have calculated the diameter of rod A and rod B, and we have considered the tensile failure of rod A and rod B. Of course, as we have applied a tensile type of force. Okay, so one more possibility is there, a failure of a spigot in tension along this cross section XX. Okay, so here I am going to consider that after the application of force of magnitude P, the rod is going to fail in a tensile manner. along this cross section. Here you can see that along the cross section XX. So along this cross section I am going to calculate the area, because the formula will be sigma T is equals to, again, sigma T is the induced tensile stress, is equals to P upon P is the applied force upon A. So let us calculate the cross sectional area. So here you can see that the after the failure the rod will look like this. Okay, so here the outer diameter, this is not the rod, actually it is the spigot. So outer diameter of the spigot is actually it is represented by D2. Here you can see that the spigot is having outer diameter, it is D2. In this view you can see the outer diameter. So this will be the area under tension. So this is the area under tension. So let us calculate this area. So outside diameter of circular spigot is D2, and it is having some hollow portion, or it is having a slot of thickness T and height D2. Okay, so this let me highlight this area. We are going to calculate this area. Okay, so this is the portion which will be subjected to tensile force. Okay, so we are going to calculate this area. So let us calculate this area. This area will be, of course, the outside diameter is cross sectional area of the rod or of the spigot end. It will be pi by 4 D2 square, minus, we need to minus this area. We need to reduce, we should not consider this area, because it is the hollow part which inside which there will be a cotter. Okay, so let us calculate the area. It will be pi by 4 D2 square minus this area of this slot. It will be D2 into T. So area will be pi by 4 D2 square minus D2 into T. Okay, so here the formula will be sigma T is equals to P divided by pi by 4 D2 square minus D2 into T. Okay, so here we can convert this, rewrite this equation in terms of D2. Okay, and we can calculate the D2, that is the outer diameter of spigot. Here you can see that, but we should have the value of T, that is the thickness of the wedge or thickness of the cotter. Okay, so the thickness of the cotter, it can be calculated by using the empirical relation. Okay, so thickness can be calculated, T is equals to, by using the empirical relation, T is equals to 0.31 D. Okay, so D is the diameter of rod A and rod B of the spigot and socket, that already we have calculated in the previous slide. So once you will calculate the diameter of rod A and rod B, you can calculate the thickness of this cotter. Okay, and put the value of thickness in this equation. You have to put the value of sigma T, that is permissible stress in tension for the spigot. Okay, for the spigot material, and P is the applied force. Then in this case only D2 we need to calculate, and we can calculate D2 by using this equation. Okay, next is the as we can see that after the application of force, there is a possibility of failure of spigot in the tension along the cross section XX, we have seen in the previous slide. Similarly, there is a possibility of socket also. There is a possibility of failure of socket along the section XX. As here you can see that this is the socket portion inside which the spigot is going to fit. Okay, so already we have seen, we have considered the tensile failure of socket spigot along the cross sectional area XX. Once again I am going to consider the tensile failure of socket along the area XX. So let us consider the tensile failure of socket along the area YY, not XX. Okay, so here you can see that the socket is having a hollow circular shape inside which the diameter it is represented by D2. D2 is also the diameter of it is the outer diameter of a spigot, that already we have seen how to calculate D2 in the previous slide. Okay, so here once again I am going to consider the tensile failure of socket. So the induced tensile stress will be sigma T is equals to P by A. So here I am going to calculate the cross sectional area A along XX plane. Okay, so here you can see that after the failure the area will look like this. Okay, so this is the area under tension. So I am going to calculate this area. Okay, and this is having some inside diameter, it is D2, which we have already calculated. How we have seen that how to calculate D2. D2 is the outer diameter of spigot and it is the internal diameter of socket, and it is also having some slot some cavity at here. Here you can see that we need to deduct that cavity, area of that cavity from the total area of the spigot. Here the total area of the spigot will be pi by 4. We need to consider the outer diameter of spigot. Here outer diameter of spigot is it is d1. Here you can see that. So along this cross section, from this point to this point, it is the outer diameter of spigot, it is d1, and we need to deduct the inner diameter, which is d2. So the area will be pi by 4 d1 square minus d2 square minus again we have to deduct the slot. There is a hollow cavity provided inside the socket and spigot also, inside which the cotter is going to fit. Okay, so we need to deduct the thickness of the same area, and we have to consider the d1 and d2. Okay, so the area of this slotted portion will be d1 into t minus d2 into t. Okay, the formula will be area A is equals to pi by 4 d1 square minus d2 square. It will represent the total area of this hollow portion, and again I am going to deduct the slotted portion out of that from that area. Okay, so the slotted portion it will have the area, it is having the area of d1 into t minus d2 into t. So I am going to deduct this from the total area, cross sectional area of the hollow part. So it will be d1 minus d2 into t. Okay, so let me put the value of area in this above equation. It will be sigma t is equals to p divided by pi by 4 d1 square minus d2 square minus d1 minus d2 into t. So already in this equation we can calculate the outer diameter of the spigot, that is d1, because already we have calculated the d2, which is the inner diameter of spigot, and it is a socket, and it is also the outer diameter of spigot. Here you can see that d2 is the outer diameter of spigot, and it is also the inner diameter of socket. So in the previous slide we have we have seen that how to calculate d2. Once you will calculate d2, put the value of d2 in this equation, put the value of t, put the value of P, that is applied force, and put the value of sigma t, that is permissible stress in tension for the material of socket. Okay, so we can rewrite this equation in terms of d1, and we can calculate d1, that is d1 is nothing but the outer diameter of socket. So by using this equation we can calculate d1. Once we will calculate d1. Okay, the next is we can calculate the remaining part or remaining dimensions of socket and spigot. Okay, here you can see that the socket is also having the collar, and the collared portion, it is represented by d4, it is having the diameter d4, and spigot is also having the collar. Here you can see that the spigot, this is the portion of spigot, and it is also having the collar, it is represented by d3. So we can calculate the diameter of collar of spigot, and we can calculate the diameter of collar of socket. So by using the empirical relation, the diameter of collar of spigot d3, here you can see that this is the diameter of collar of spigot. It will be calculated by using the empirical relation. d3 is equals to 1.5 into d. Here small d is the diameter of the rod A and rod B for the socket and spigot. Okay, and that already we have seen how to calculate small d in the first slide. Okay, next is d4. It is the diameter of collar of socket. This is the diameter of outer diameter of collar of socket. It is represented by d4. You can see that, and can be calculated by using the empirical relation. d4 is equals to 2.4 times small d, and again small d is the diameter of rod A and rod B of spigot and collar. Okay, so here by using this equation we can calculate d1, that is the outer diameter of socket, and by using this empirical relation we can calculate the diameter of collar of spigot and socket. Similarly, we can calculate the remaining dimensions, that is the thickness of width of this portion A, okay, from along the axis for the spigot, and C for the spigot also, for the same spigot. It is the distance from the slotted portion or slotted wall, from the wall of slotted portion to the portion where the actually collar starts. So this width, it is represented by C, and the portion which is from the end of one end of the spigot to the hollow part along the axis, which is measured along the axis, it is represented by A. So A and C will be equals to 0.75 into D, where again D is the diameter of rod of socket and spigot, which is already we have seen how to calculate D. Once you will calculate D, you can calculate A, the value of AC. It will be 0.75 into D. Next, in this slide, I am going to discuss about the design of cotter. Already we have discussed about the design of socket and spigot. In the tensile manner they can fail, and we have seen how to calculate the various dimensions of spigot and collar. Okay, in this slide I am going to discuss about the design of cotter. There is a possibility of failure of cotter in shear manner. Here you can see that after the application of force of magnitude P on the socket and on the spigot, here you can see that there is a possibility of failure of cotter in a shear, double shear manner. There is a possibility here along this plane and along this plane. Okay, I have highlighted after the application of force in a tensile manner. The cotter can be, it will be fail in a shear, double shear. So this area at this portion and this portion we need to consider to calculate the shear stress. This shear stress, induced shear stress tau will be equals to P by A. Here double shear failure is there. You can see here, you can see that when a force of magnitude P will be applied on socket and spigot, okay, there is a possibility of failure of cotter along this plane. So there will be a shear stress along this plane and along this plane. So there is a double shear failure. So let us calculate the area under shear. Area will be equals to BT. Okay, again here I have multiplied the area by 2 because here double shear failure is there, and the area will be, again here we need to consider the mean width. The mean width is of cotter. It is B. It is represented by B, and the thickness, it is T. So this is the area under shear. Okay, B into T. Okay, again because of double shear failure is there, I have multiplied the area by 2. Okay, so tau will be equals to P divided by 2 BT, where B is the mean width of cotter and T is the thickness of cotter. Already we have seen, we have calculated the thickness of cotter, and by using this formula we can rewrite this equation in terms of B. It will be B is equals to P divided by 2 tau into T, and tau is the permissible shear stress for the material of cotter. Okay, so by using this equation, that is equation number 4, we can calculate the width of cotter. Okay, so but you should have the value of permissible shear stress, that is permissible stress in shear for the material of cotter. Obviously the value of P, which is the applied force, and T, which already we have calculated by using the empirical relation in the previous slide. That is nothing but the thickness of this cotter. Okay, here I am going to consider the failure of cotter in bending. In the previous slide we have discussed about the failure of cotter in shear. Okay, when the cotter will have loose fit with spigot and socket, there is a possibility of failure of cotter in bending. It will increase the possibility of failure of cotter in bending. Okay, so let us calculate the bending moment. I am going to calculate the bending moment along this plane, along this point and along this point. Okay, let me show you this. So I am going to calculate the bending moment. Obviously it will be maximum at the central portion of the cotter. Here you can see that the middle part of the cotter, it is actually this portion of the cotter, it will be inside the spigot, and spigot is having the outer diameter D2, and the portion of the cotter, outermost portion of the cotter, this is the outermost portion. Okay, this portion of the cotter, it will be inside socket, and socket is having the outer diameter D4. Okay, so here you can see that this portion, it is subjected to uniformly varying load, which is actually inside the socket, and the portion which is actually inside the spigot, which is shown by the yellow color. Okay, so this is the portion, it is actually inside the spigot. It will be subjected to uniformly distributed load. Okay, so here you can see that this is the uniformly distributed load. Okay, so here I'm going to calculate the dimension Z for the spigot, and also I'm going to calculate the dimension X. This is the dimension X for the socket. Okay, so here you can see that I have redistributed the load. Here you can see that I have redistributed the load at this point and at this point. I have taken the magnitude P by 2 and P by 2. So I am going to calculate this distance. Here you can see that this is the 1/4 of, I have, here you can see that there are 4 equal parts of d2. Okay, so the value of z will be d2 by 4. Okay, the value of z will be d2 by 4, because while calculating the bending moment along this plane, I should have the value of z. Next is I'm going to calculate the value of x. Here you can see that x is, the portion of x is, it is 1/3 of y. Okay, here you can see that it is 1/3 of y, and y is the portion, or it is the thickness which will be inside the socket. Okay, so here x will be 1/3 of y. Again I need to calculate the y. Okay, so here you can see that y, this is the y. Okay, so y is nothing but it is the difference between d4 minus d2 by 2, or it is the radius of d4 by 2 minus d2 by 2. When you will deduct the d2 by 2 minus d4 by 2, you will get y. Okay, so y will be, the value of y will be equals to d4 minus d2 by 2, and x will be equals to, x is equals to y by 3. Okay, so let us calculate first of all x. It will be 1/3 of y. Okay, and y will be d4 minus d2 by 2, so it will be d4 minus d2 by 6. Similarly z, let us calculate z. I have shown here at here. You can see that z is actually 1/4 of d2. Okay, so z will be equals to d2 by 4. Okay, so let us calculate the bending moment. Okay, I'm going to erase this. So let us calculate the bending moment. So here I am going to calculate the bending moment along this line. Okay, along the center of the cotter. Okay, so here I am going to consider that the forces which will try to create a clockwise bending moment, I am going to consider them as a positive, and the forces which will create the anti-clockwise bending moment, so these are the forces along this plane, they will create the anti-clockwise bending moment, I am going to consider them as a negative. Okay, so the bending moment mb will be equals to p by 2 into we need to consider this distance. Okay, this distance is actually, it is d by 2 plus x. Okay, so this is also x, and this is actually d by 2. Okay, so it will be d by 2 x plus x. So p by 2 multiplied by d by 2 plus x, and b will be equals to p by 2 multiplied by d by 2, d2 by 2, sorry, not d by 2, plus x. Similarly, this force is actually creating an anti-clockwise bending moment in a vertical manner. Here you can see that p by 2 multiplied by this distance is actually, this is the distance z. Okay, so this distance, here you can see that this is the distance represented by letter z. Okay, so it will be p by 2 multiplied by z. Here you can see that. So already we have calculated the value of x, it is d4 minus d2 by 6, and z it is d2 by 4. So let us put the value of x and z in this equation. It will be mb equals to p by 2 multiplied by d2 by 2 plus d4 minus d2 by 6 minus p2 by 2 multiplied by d2 by 4. Okay, so after simplification, I have taken the p by 2 as a common. It will be again I have multiplied the numerator and denominator by 2. It will be 2d2 by 4 minus d2 by 4, this d2 by 4, plus these terms d4 minus d2 by 6. So it will be mb will be equals to p by 2 into bracket d2 by 4 plus d4 minus d2 by 6. Okay, so let us calculate the bending moment. As we know that the bending moment, it is represented by sigma b is equals to mb into y by I. Okay, so here mb is the bending moment, which already we have seen how to calculate bending moment. We can calculate the bending moment by using this formula. Here p is the applied force, D2 is the diameter of spigot, that outer diameter of spigot that already we have calculated in the previous slide. D4 is the diameter of socket that also we have calculated in the previous slide. Okay, so once you will have the value of D2 and D4, you can calculate the bending moment, and by putting the value of P you can calculate the bending moment. Here Y is the distance of extreme fiber. Okay, so let me show you how the extreme fiber is actually located. Here you can see that this is the neutral axis. Okay, this is the neutral axis. Okay, along this there will be a bending. These fibers, the lowermost fibers are these fibers will be subjected to tensile stress, and upper fibers of the cotter will be subjected to compressive type of stresses. Okay, so the distance between this is also represented by the letter Y. Here I have represented the horizontal distance by using the same letter, so this is also Y. Okay, so Y will be actually, it will be half of B by 2. So here for this for the bending moment, Y will be actually equals to, it is B, that is the width, average or nominal width of the cotter divided by 2. Okay, so Y will be B by 2, and I is the moment of inertia for the rectangular cross section having width B and thickness T will be TB cube divided by 12. Okay, so here after putting the value of Y, MB and I, you will get the induced stress, bending stress. Okay, so I have written the equation here. Sigma B is equals to P by 2 multiplied by D2 by 4 plus D4 minus D2 by 6 multiplied by the value of by Y is here. Y is the distance of extreme fiber from the neutral axis, and here Y is the half of the width of the cotter, so it will be B2 by 2, and width of the cotter is B, and I is the moment of inertia for the rectangular cross sectional area. Moment of inertia is TB cube divided by 12. Okay, so by using this formula you can calculate the bending stress, or by using this formula you can calculate the width of the cotter. Already in the previous slide we have calculated the width of the cotter B by considering the shear failure of cotter. When you will have the value of sigma B, that is permissible bending stress for the material of cotter, P is the applied force, D2 is the outer diameter of spigot, D4 is the outer diameter of socket, B that we are going to calculate, T is the thickness of the particularly this spigot, and we can calculate the thickness by using the empirical relation. So once you will put all these values, you can calculate the B, that is nothing but the thickness of width of spigot. So we can calculate the width of spigot by considering the shear failure of spigot, and we can calculate the width of spigot by considering the bending failure of spigot, and we are going to select the maximum value which will come among these two. Okay, so we are going to select the maximum maximum value of B, that is the width of spigot, among these two, that is the width of spigot according to the shear failure and width of spigot according to the bending failure. Okay, now let us discuss about the failure of spigot end in shear. Already we have calculated the various dimensions of spigot, that is we have calculated the outer diameter of spigot D2, okay, in the previous slides. Okay, we have calculated the thickness of end, that is A. Okay, so for whatever the calculated dimensions, I am going to check that whether the design is shape in shear or not. Okay, shear and crushing. Okay, so here you can see that when a force of magnitude P will be applied at the end of the spigot, there is a possibility of failure of spigot end in a double shear. You can see that when a force of magnitude P will be applied along this direction, okay, and also along this direction, there is a possibility of failure of spigot along this plane in a shear manner. Okay, so you can see that the shear failure of spigot is shown at here in the top view, and this figure you can see that. So we need to calculate this area under shear. So the induced shear stress will be tau will be equals to P by E, but here I am going to consider the double area because double shear failure is there, and the shear failure will take place along two planes. you can see that it will take place along this plane and also this plane. Okay, so we need to consider the double area. So area of this portion, it will be equals to we need to consider the diameter of the spigot, that is d2, and for the width we need to consider the width of the end portion, which is a. Okay, so the area of this a single shear area will be d2 into a, so the double shear area will be tau is equals to 2 into a into d2. So here we can calculate the induced shear stress once we after the calculation of the dimension a and d2, we have to put the dimensions of a and d2 in this equation. We have to put the value of applied force. We can calculate the induced shear stress, and if suppose the induced shear stress will be less than the permissible one, the permissible one will be given in the design data book, or it will be given in the problem for the material of spigot end. Okay, so if for the calculated dimensions, the induced stress, that is tau, will be equals to the permissible shear stress, then our design will be safe. Next is there is a possibility of failure of spigot end in crushing manner. Okay, so here you can see that after the application of force in this figure. Okay, so let me show you in this portion, and this portion will get crushed because this hollow portion, inside this hollow portion there will be a wedge, there will be a cotter. Okay, so the cotter after the application of force P, the cotter will apply a force of equal magnitude along this wall, and this portion it will get crushed. Okay, so we need to calculate the area under crushing. Sigma ck will be equals to P by A, and area under crushing it will be here you can see that the area which will be get crushed, it will have the thickness T, and the through diameter, the whole diameter of the inside portion of the whole diameter of spigot can get crushed. Okay, so the crushing area will be equals to T into we need to consider the diameter of spigot, that is d2, because this portion, okay, let me highlight this here. You can see that this portion it can get crushed. Okay, so we need to calculate the area under crushing. So the maximum I'm going to consider the total diameter. So this is the diameter of the spigot, which is d2, and we need to consider the thickness of cotter, and thickness of cotter is T. Okay, so the area will be d2 into T. So sigma ck will be equals to P divided by T into d2. Once again we have to put the value of P, which is already provided, which will be provided in the problem. T is the thickness, which already we have calculated, thickness of the cotter. D2 is the diameter of the spigot. So we need to put all these values, and we have to check that whether the induced crushing stress is less than the permissible one. In the problem or in the design data book, we can get the permissible crushing stress for the material of the spigot end. Okay, or in the problem it will be given. Next is the shear failure of socket end. Okay, so here you can see that as the spigot can fail in shear, the similarly in the similar way after the application of force of magnitude P, there is a possibility of failure of socket. So this portion of the socket can get tear off. Okay, this portion and this portion of the socket. So we need to calculate after the application of force, when a force of magnitude P will be applied on the socket and on the spigot. So here you can see that this portion can get tear off. So here in this figure we need to calculate the area of this portion. So the area of this portion will be equals to d4 pi by 4, d4 again not pi by 4. Okay, it is the rectangular part. Okay, so it will be d4 into c minus d2 into c. So the shear stress, induced shear stress tau is equals to P by A. Again here you can see that a double shear failure is there in this figure. You can see that shear failure takes place along two planes. Okay, so the area will be 2a, tau is equals to, and the area will be d4, that is the outer diameter of the collar of the socket, minus d2, that is nothing but the inner diameter of the socket, and it is also the outer diameter of spigot. Okay, so it will be d4 minus d2 multiplied by the thickness. So thickness of the collar, here the collar thickness is actually it is c. Okay, so we need to consider this collar thickness c. So it will be d4 into c minus d2 into c. Okay, so the formula will be tau is equals to P divided by 2 into bracket, because I have multiplied the area by 2 because double shear failure is there. So tau is equals to P divided by 2 into bracket d4 minus d2 into c. Okay. Okay, so here we need to put the values of D4, that is outer diameter of collar of socket. D2 is the inner diameter of socket, or it is also the diameter of spigot, and C is the thickness of this end. Okay, so once you will put all these value, you can get the induced shear stress, and again you have to check that whether the induced shear stress is less than the permissible or not. If it is less than the permissible, then our design is safe. For whatever the calculated values of D4, D2 and C, our design will be safe. Okay, or by using this equation we can calculate the C also, that is the dimension, end dimension of the width of the cotter, or you can call it as the thickness of the spigot collar. Okay, not spigot collar, socket collar. Next is the crushing failure of the socket end. Here you can see that similarly, in similar way as I have discussed regarding the spigot, there is a possibility of crushing of spigot along this plane. Similarly, there is a possibility of crushing of a socket. Okay, this portion of the collar of socket can get crushed after the application of force of magnitude P. So we need to calculate the area of this portion, okay, which will be under crushing. So sigma Ck will be equals to P by A. Sigma C is the crushing stress, P is the applied force, and A is the area under crushing. So here you can see that I have shown the area under crushing. So the area under crushing will be again the thickness. We need to consider the thickness of the cotter, and we need to consider the outer diameter minus inner diameter of the collar. So outer diameter of collar is D4 minus inner diameter. I'm going to consider deduct the inner diameter, D2. So it will be D4 T into D4 minus T into D2. Okay, so formula will be sigma Ck is equals to, that is sigma C is equals to P divided by T into D4 minus D2. Okay, so here again we can calculate the induced crushing stress. Okay, and we need to check that whether the induced crushing stress is less than of the permissible one or not. If it is less than the permissible one, then our design will be safe. Next is we can calculate the thickness T1, that is the thickness of T1 is the thickness of the collar, okay, of the spigot, by using the empirical relation 0.45 into D. Okay, so here D is the diameter of rods, so A rod A and rod B of the spigot and socket. Okay, and the taper for the cotter, you can see that there is a taper provided, and taper will be 1 in the 32. Okay, so this is the total design procedure of cotter joint. Okay, thank you.